Now, just as a quick recap, we remember that when we have the electron excited too far, that it will just disappear, and so that's the ionisation energy. So the atom becomes an ion because it's lost an electron, and it's when all these the lines stop, so we know that the wavelength is here. That's when you've added too much energy and it won't come back and it heads off into space. And so the actual definition you need to know. The definition, it's better to be able to write this out because this also gives you a good definition if it's written out correctly. And so as it's a formula, these represent 1 mole. So it's 1 mole of atoms converted to 1 mole of ions by removing 1 mole of electrons, and it's in the gaseous phase. All right, so the energy required to remove 1 mole of electrons from 1 mole of atoms or ions in the gaseous phase is the first ionisation energy. So make sure you can write that out exactly and read it off as a definition. So we need to be able to explain this full diagram here, and there's 4 things we need to note. So the first trend we're going to do is the group trend. So if you look down group 1, hydrogen, lithium, sodium, look down the first group, you'll see that it's just these ones here, and you could look down one of the other groups if you wish, and you can see it's generally decreasing. Okay, and so that is because they're in larger shells. Now, next unit topic, I'll talk about this a little bit more. That actually should be slightly larger. So there's a conflict. It's also a larger nuclear attraction, but it's a greater distance, and you'll see from a balloon demonstration again, that distance is exponentially more important than size of charge. So the force of something is it's always much, much greater. So the effect of the distance is much, much greater than the effect of increasing the force. And so what you effectively have is, as you go down, it's easier to remove the electron because the effect of nuclear charge is decreased. There's also increased nuclear shielding. So that's avoiding the attraction between the negative and the positive. Okay, so for that reason, it is easier and easier as you go down a group to remove an electron. So the first ionization energy decreases. Okay, will be touched on again in all of this will be touched on in next one, but we're doing calculations, so we need to just have a good idea of what's going on here. So the periodic trend is a little simpler. The general trend is it's getting harder and harder. That's easy because they're all in the same shell, so they're all the same distance around the nucleus, but the nuclear charge is increasing as you go across the period, and so of course it's harder and harder to remove the first electron from an element as you go across. So ionization energy increases across a period. Now the shells also, which we've talked about before, these large jumps are because this is in one shell and they're a lot harder to remove. But when you jump to another shell, it's a long, long way away with only 1 proton increase, but a huge distance increase, and so it's much, much easier. So they indicate the shells, these large jumps, the energy levels. Now, we're just going to do the 2 exceptions as well. And so you can see that this one slightly decreases. And that's because it is a lot easier to remove an electron from this because it's in a new subshell. Not a complete shell, but a new subshell. And so there's also a little bit of electron shielding. And so this is closer to the nucleus, so it has a slightly stronger pull to it. This is slightly further away from the nucleus, so it's slightly easier, so that's why it drops. And the other 2 exceptions are these ones, and these ones are halfway through the P's. And so they are the same distance, but we have the mutual repulsion, so it's easier to remove electron from the oxygen and the sulfur here because of the mutual repulsion effect. Okay, so that hopefully explains every little detail of the first ionization energy. We'll do successive ionization energy to finish off the topic, but we need to do the calculations as well. And so these formulas are from the data booklet. You just need to remember that you'll always know the C, speed of light, and the H from the data booklet. And so if you're given one of the F or given one of these, use this formula. If you're given one of these, you can use this formula depending on what the question is. And so we'll just do 2 example questions. Determine the energy of photon of red light given the wavelength is 650 nanometers. So if you go to your data booklet, you'll know you've got the C and you've got the wavelength, so you can get the frequency. Then you'll be able to do the energy. So speed of light from your data booklet, and that's from the question. So you get this as the frequency, which is a very, very small frequency, but that's a very, very large frequency, a lot of cycles per second because it's a tiny, tiny wavelength. And so then the energy is just subbing those values in, Planck's constant, and you've got the frequency, and so it's a very, very tiny amount of energy for just one photon. And the more common and logical question is a little bit harder, is to tell me the actual ionization energy from the wavelength. So we know the wavelength as the maximum wavelength that's for ionization energy. So what is the actual ionization energy value? So we follow the same format that we did last time, and so we've got the frequency and we've got the energy. The only thing we need to do now is, because the ionization energy is 1 mole, is work that out for an entire mole, not for just one photon, but a mole of things. And so there are 6.02 by 10 to the 3 moles, photons per mole, and you already got the energy for just one photon. So you just times them together. It's down to 3 sig figs here, and so the ionization energy is 1,310 kilojoules per mole, which is quite clever, really. Hope you enjoyed that.